Okay, hi everyone. Good afternoon. Welcome to our seminar series for this quarter. For those of you that do not know me, my name is Miguel Jaller, and I'm gonna be the instructor for the seminars this quarter. So welcome again. I think we're gonna have a pretty good lineup for this quarter, starting with today's presentation. Before we start, reminder, you already did it. You're gonna be doing iClicker or saying if you're here or not. There are a few QR codes around there, so just try to do it. Another advertisement. There is another QR code here if you want to register for the EJ closing ceremony. That is gonna be next week, next Thursday. So remember to do that if you're interested. So we're gonna be again meeting every Friday at 1:40 for 1 hour presentations, and then hopefully we have pretty enjoyable conversations and discussions of the different topics. Today, I have the pleasure of having Alvaro Cardenas from UC Santa Cruz. Professor Cardenas was a professor at UT Dallas, also postdoctoral researcher at Berkeley, and also worked in the private sector. I was award-winning author and scholar, and working in different topics from the computer science and now an intersection with transportation. So today we're excited about this topic of how to avoid risk and improve the security of autonomous vehicles. So we're all yours. Thank you for coming.
Yeah, thank you for the introduction, and thanks everyone for coming and inviting me to UC Davis. So yeah, my name is Alvaro Cardenas, and I am a professor in computer science and engineering. So maybe, I don't know, I might be working on the topics that might be a little bit off, but it's still at the intersection of hopefully things that you are interested in transportation. So so the talk I'm going to be focusing today about our work in securing autonomous vehicles, drones, things like that. And the motivation for this is, so control systems have been evolving through the years or through the centuries, I would say. So like the steam governor is one of the famous first control systems, automatic control system that is an analog control, right? So it's very, like if you're an attacker, I think unless you have physical access and you do something that requires a lot of effort, you don't have to. It's harder to attack. But nowadays, vehicles, the modern car is basically a computer with wheels, right? So it has the same attack surface of any computer. And a computer has two, I guess, things that make it easier to be attacked. The first one is it can be reprogrammed to do anything. Like if you could attack the steam governor, you could. I mean, it's not what we call in computer science a universal machine or a universal Turing machine. It's only meant to do one thing and one thing only. A computer can do basically any computable function that you want. So you can reprogram it to do things if you get access to it. And the other advantage from an attacker's perspective is that you don't necessarily have to be physically present. You can potentially compromise the supply chain or through remote mechanisms, because a lot of these have connectivity. You might be able to exploit it. So that's why we're now interested in the security of these systems. And there's been already attacks to navigation and control systems. So there's been a lot of GPS spoofing attacks usually in the Black Sea or in China nearby. There's been spoofing attacks that people haven't really found. The reason they say, well, there's maybe experimental systems that are being deployed by, for example, Russia or things like that. But there've been sort of, for example, captains of ships are navigating, and then all of a sudden they appear in the middle of an airstrip, right, or something like that. So GPS spoofing. There's also researchers that show that these vehicles or modern vehicles are attackable. So there's a famous example, maybe now it's 10 years ago, but researchers that were able to, through the telematics of the system, attack a remote Jeep. And you can look online a video of a Jeep, and Andy Greenberg, who is a reporter at Wired, like driving it and the hacker showing, okay, yeah, now we can, for example, disable the braking system. Now we can turn on your radio. Now we can. And he actually recorded that on a video, and so that's another example. And yeah, so there's many attacks like that, and perception attacks as well. So so there's again, this is mostly research. Not sure if we have seen any of this in the wild, but researchers showing, for example, physical attacks that you can sprinkle some like white dust near like intersect or lines in a highway, and then full autonomous driving systems to start steering one way or the other because they think the lane is shifting. And then there's also this like literature in the computer security community that talk, for example, of analog attacks. So the classic example, or how this literature started, was how like they found out that if you put a loudspeaker in a drone, so for example, before the drone takes off, you put like a radio in or something like, and then you start blasting music when the drone is flying. If you blast specific sounds at some resonance frequency of the IMU, or like the inertial measurement unit of the drone, then you would interfere with the self-stabilization of the system, right? So because the perception will be basically attacked by these systems. And then after that, there's been a lot of attacks, sort of like electromagnetic waves and all sorts of, like there's also attacks, like heaters that change. So they make basically, they affect perception. So the measurements that you get from the real world are perturbed by the attacker, and you can then, an autonomous control system will then make incorrect control decisions because it's getting false information about the real world. So with that in mind, so what is security? So a lot of people think that security is about preventing these attacks, and it's true. I would say about 30% of security is about that, preventing. So how can we design systems to prevent someone from launching this type of attacks? But security is not only that. You also have to spend a lot of effort in detecting. So one of the maxims in security is that there's actually theorems about it, that you say, well, you cannot have something that is 100% secure because, like, for example, if you were to write software that detects with 100% accuracy malware, it's actually one of these impossibility results in computer science, that you cannot do that 100%. You can make an equivalent, show that this is equivalent to solving the Turing, like the halting problem, which is one of these things that is considered impossible in computing. So yeah, you can, in theory, you cannot have sort of like something that is guaranteed to be 100% secure. So you always have to understand that your system is eventually potentially going to be attacked. I mean, there's somewhere that your system is going to miss. The attacker is going to get in, so you have to detect. And once you detect, what do? You have to respond, right? So a lot of security is, yeah, about first identifying the problems and protecting. So that's the classical, or the way people identify security more. Like you want to prevent these things, but then you want to detect and then respond and recover to attacks. And that's sort of like the line of work I want to discuss. So I'll be spending about 20 minutes talking about our work on preventing attacks. Then very briefly about detecting attacks, because this is now kind of getting old work, but it's a motivating point for responding automatically to attacks. So that's sort of like the agenda for today. And feel free to, I don't know how you run the seminars, but if you want to interrupt me in the middle, feel free to do so if you have any questions. So okay, so preventing attacks. So the first step. So there's many ways to preventing attacks. What we're going to focus in this talk is about testing autonomous vehicle stacks to potential attacks. And the potential attacks that we're going to be looking at in this case are attacks to autonomous vehicles, physical attacks in this case, So like Waymo bullying, there's suddenly a trend. So I don't know, I think Sina actually sent me a video of someone attacking her car at some point. And like there's videos of, for example, people would put a cone in front of a vehicle, and then the vehicle will think, oh, I need to stop. There's no, and yeah, so protesters armed with traffic cones immobilizing drivers' cars. And the question is there a way to prevent this type of attacks, to be sort of like aware and then try to make sure that attackers don't exploit them? So the goal is to find maybe exploitable vulnerabilities in vehicles before we deploy them massively. And to find these exploitable bugs in an autonomous vehicle stack, you can either use large-scale testing or diverse scenario testing and discover, in this particular talk, what we call adversarial maneuvers. And what do I mean by an adversarial maneuver? So imagine there's a person driving, and the attacker has, like, the objective of the attacker is to make, for example, autonomous vehicles crash. Like, they don't like they are upset that all these robots are invading their city, and they decide, you know what, whenever I see one of those, I'm gonna drive aggressively, and hopefully they crash. And the goal of the attacker is to, in this case, wants to maybe find an adversarial driving maneuver that will create a crash. But if the attacker crashes, in this case, the attacker is the red one. If the attacker crashes, like, he doesn't like that because he loses, right? If he drives aggressively and nothing happens, then the attacker also loses because nothing happened, right? But if the attacker is able to drive somehow in a way that makes the autonomous vehicles crash, then the attacker wins. So the attacker has two objectives. One is to make, in this case, other vehicles crash or get into an accident, right? Violate the safety of the vehicles. And at the same time, it doesn't want to be involved in the crash, right? It wants to maybe cause something and then continue to run away. And the first question is this possible? And if it is possible, how can we discover how can these attacks happen? So yeah, so there's many ways to try to test autonomous vehicle stacks. And you have formal methods, and you also have large-scale testing, right? So you put your autonomous vehicle stack in a scenario where you test multiple different scenario cases, and then you try to see if it satisfies or if it passes all the test cases. Falsification of cyber-physical systems is one area that tries to bridge these two. Formal methods is sometimes hard because, right, there's a lot of abstractions that you have to make about the system to create a mathematical model, and then it's hard to prove that. But falsification tries to merge these two fields, because what you want is to write a formal specification of what you don't want it to happen. So let's say I want safety, and safety means that you define precisely what you mean by safety. But then you don't have to model precisely the dynamics of the vehicles, and you don't have to model the control theory aspects. You just test. You say, well, I just have my specification, and then I just test it. But I test it in an intelligent way. I test it in a way that is trying to, every time I create a new scenario for testing, and in this case, the scenarios are going to be in a simulation, because we cannot have, if we want to run thousands or millions of scenarios, we cannot do it in the real world. First, we have to start with a simulation. So in this case, we're going to test it in a way that we try to violate the formal method. So we have a specification, and then we convert that into an objective function and like an optimization function, and then the optimization technique or the sampling technique that creates the scenarios is going to try to find cases where this metric or this specification is going to fail. And if in this case, we have for cyber-physical system falsification, we have a system S with inputs U and a formal requirement F, and the goal is to find an input such that this input violates the requirement. In this case, if we define, I want my vehicles in this platoon to always be safe and never crash. And if the attacker is able to find a way to crash them, then we output that as the example of the specification. And as I said before, classification is using a theory that translates this formal specification into an optimization function. And then we run an optimization approach on it to try to find it. And so, yeah, so I guess I'll skip through some of the mathematical details, but the idea is to use, to formally specify the safety property. We use metric temporal logic that it basically extends like the classical logic with operators like until or eventually or always. And then our goal is to convert this specification into an objective function, and this is called the robustness metric. So we're not the first ones who did that. There's a theory about it. So we're just applying the theory for finding this changing. First, once we define our specification, we use this theory to change it into an optimization problem. And the goal is for us is to define the formal description. So we say our goal is that the distance between any two vehicles, I and J, is greater than the safe distance. So basically, we don't want them to crash. And the attacker in this case has two objectives. So other vehicles other than myself will eventually crash. So we write that in as a formal specification. And we want also the attacker safety is that the attacker does not crash. That's what it wants. So the attacker can only control one vehicle, right? And in this case, in general, we can consider many scenarios, like maybe aggressive driving, like crossing in front of someone else. To start our work, we said, well, let's start simple. Let's say we're just gonna let the attacker change the throttle, braking. But I guess the steering is future work. We don't have that. But throttle braking. So you accelerate and you brake, and you let the attacker change those parameters. And based on some acceleration and braking pattern, then maybe you can make other vehicles crash. So basically we run this in a simulator. I don't know if some of you are aware of Carla, or if anyone is using it for some of you. Yeah, okay. So Carla is basically a high fidelity simulation that you can actually put autonomous vehicle stacks like AutoWare on top of the vehicles, and it's a simulation driven by, I believe it's the Unreal Engine, I think. So it's basically like you're playing GTA, but for research, like Grand Theft Auto. But the physics are more accurate than the video game in theory. Because Carla is developed by a team of researchers that is trying to basically do a high fidelity simulation of several traffic conditions, including autonomous vehicles. And so we have we create controllers of the victims, or in this case, the autonomous cars, and the attacker controller that we're gonna let the throttle and the brake change in our simulation, in our system, and then we integrate this in Carla in this particular case, and then we see if we satisfy the property or not. And if not, then we change the attacker's controller and we run another simulation and so on and so forth until we get the counter examples. The brake intensity, brake time, and so to start, we use some basic optimization approaches. So basically samplers that are trying to optimize this objective function. So Bayesian optimization builds a probability model of the objective function and then samples the function to find the maximum values. And cross entropy estimates rare event probability, and it gradually changes the sample distribution to find the desired event. So in this particular case, we have the attacker and the distance. And we implemented, the details are in the paper if you're interested, but we implemented basically an adaptive cruise control mechanism found in a couple of papers in these three vehicles, and then we let the attacker accelerate and brake with a particular pattern. So each vehicle will use a switching controller, cruise controls, and then adaptive cruise control to preserve velocity and distance when it reaches. So when the vehicle is far away from another vehicle, it just cruise control. So it wants to reach a speed, and then it switches to adaptive cruise control when it's closer than a certain distance. So this is how the simulation looks in Carla. So we have an attacker and we have vehicles behind it. And we assume that the victim vehicles are unable to change lanes due to traffic in this particular case. And we consider two attack signals with different parameters. We let the attacker, for example, do something like this. And we let the sampler figure out how many times am I going to accelerate and then brake and the intensity of it. Or if I'm going to do it only once, I'm just going to accelerate and then brake. So it can be sort of like repeatedly doing acceleration or braking multiple times, and the sampler selects how many times to do it for like the intensity of each acceleration or braking. That's what we let the optimization select, that type of property, or only two, or only one time. And yeah, we found a couple of counter examples. This is a particular counter example. Here is the video. So the attacker brakes and then accelerates, and then when it is starting to accelerate, these two vehicles crash. And in this particular case, so we can see this is the distance, this is the attacker distance, and this is the acceleration. So at the beginning, it is accelerating, then it brakes, and then it accelerates again. And I think here, when it is accelerating again, after braking and accelerating, this is when the two vehicles 2 and 3 crash. So these two vehicles are here at some point, I guess at some point get to the same point in X, in the distance. And we found several counterexamples depending on what attacker, depending on the persistent or intermittent attacks, and with different optimization methods. I think the interesting thing is that we couldn't find a lot of patterns, but the interesting thing was the distance, the configuration distance of the cruise control. So it is interesting that here we have in the y-axis we have the distance of that the adaptive cruise control sets in, like how what is the set point distance that I want to have in front of the other car. And we interestingly find that it's actually, there's a sweet spot here between 5 and 7. If the set meters, if you have a longer than this, let's say 8 meters distance, if that's the set point, it is harder for the attacker to cause the crash, because I guess vehicles have a lot of leeway to brake and accelerate without crashing to each other. But interestingly enough, at the beginning we were confused. Like we thought that if the vehicles are very close to each other, they would crash all the time. So it took us a while to figure out, and I guess in retrospect, in hindsight, the solution is obvious. The problem is that the attacker always crashed also. When the set point was too close to each other, like below 4 meters, and the attacker was trying to make those maneuvers, it would always crash. So it would be hard for the attacker. I think there were some cases where it managed to create some crashes using a particular optimization, but the speed difference is not too hard. So the y-axis is the distance, the set point distance, and the x-axis is the difference in speed at which the cars crash. So the highest here is the more critical crashes, because it's, I mean, if you crash with a difference of speed of, I guess, 1 kilometer per hour, it's probably not a big issue. It's probably I just bumped someone, but you will continue, right? So in here, it's not too much. It's probably not. We don't care too much about this region. It's probably this region where we start caring a lot. So these are and all of these attacks happen in one particular set point, which was, I think, an interesting observation. So so it's so I guess this is just a description So yeah, so this is only the beginning of the work. We're currently working with several colleagues in extending this work. So this was originally some work that we did with San Jose State University and with Purdue. And we're currently continuing our work. So we have shown the feasibility of two distinct attack signals, but we're looking to expand this to other adversarial driving maneuvers. So we're right now working with having more flexible maneuvers, like if you're crossing in and out of traffic. So that's something that we're currently working on. Again, let the attacker have more flexibility. And also the other thing that we're doing right now is adding more sophisticated autonomous driving stacks. So this paper, we did it with, we implemented our own adaptive cruise control from the literature, but there's a couple of autonomous driving stacks that are open source. So like OpenCDA from UCLA, and then we have others from AutoWare that we're currently testing. So to see if those autonomous stacks are also vulnerable to these attacks. So we're gonna get more, hopefully more results like this in the future. And if you're interested, we have this scenario in the paper, or I can share with you. I think this one is published, but this one, I don't know, before this talk, I was looking to see if the proceedings were online and I couldn't find it. But if you're interested, send me an email and I can share it with you. We have the source code is open source. So if you want to play with some of these tools, let me know and I'll be happy to share. Yeah.
Was the ACC algorithm that you implemented like an IDF type algorithm, or was it more just like a set distance type algorithm?
Yeah, we implemented actually 3. There was one that came by default that was just a switching controller, acceleration and braking. Then we had a set distance controller, and then the third one was a platooning. So you would have a message passing between the vehicles to say, okay, this is the set point that I want, and the speed that we're going. So there would be a leader in the platoon that would spread.
Okay, well, I mean, some of them are string stable and some aren't. So like there might, with those algorithms, there might be like a number of vehicles following, at which point a crash is inevitable, right? Like if you went out to infinity vehicles.
Yeah.
So you had 3 vehicles, right? So
in this case, yeah,
there might be like non-AV style, just sort of dumb algorithms that are string stable where you would get better results. Just my thought.
Yeah, no, definitely. Yeah. If you send me an email, okay, we have to. Yeah, so that was preventing, and then for detecting and responding. So we also have a couple of results. So we originally have a paper in using security for basically using what we call the physical invariance of the system to detect something is off, and then how to respond to the attacks. We have a couple of papers, one in the real-time application systems conference, IEEE RTAS, and then the more recent one is a workshop that I was also looking. I couldn't find it online, so if you're interested, let me know. I can share a copy. So I think that eventually this one will get the proceedings will be published, but this is a couple of because now everyone is doing research in AI. We're also trying to work on that, but there's a logic to the madness, so I'll go into some details. But so detecting attacks. So how do we detect perception attacks into the system? So we have the control system that, as I said before, you may have GPS spoofing. So you might end up being in places where you're not supposed to be, or you might potentially have a controller that is compromised. So maybe there was a supply chain attack, and the controller that you loaded into your system was developed that had like a Trojan, right? And it's not doing what you're supposed to be doing, or an actuation attack. So as I was saying before, there's like this sort of like attacks, like with the acoustic attacks or electromagnetic interference attacks. So when you, for example, you send a control signal to the rotor of your drone, you're expecting something, but then what gets implemented by the actuator is actually different, because the actuator is getting like it's the action that the actuator is acting upon is being interfered by the attacker. So to work on this, the idea is to extend. So there's a literature in computer security, sort of like the intrusion detection, right? So there's a lot of work on detecting attacks in networks, and the difference here is to say, well, we're going to detect attacks in a cyber-physical system by using the physics of the system. And why? Because you can make a correlation, right, of what you see and what you expect. And if you start seeing things that are off, you might be able to detect attacks. And so this is similar to the literature on fault-tolerant control and robust control, things like that, right? So you want to be able to detect, for example, if a system is failing, and how do you detect that when basically the system is not following what you expect it to follow. But you of course need to have a good model of the system. In this case, you need to have here, you have the classical control loop, where you have actuators, the physical process, and sensors, and a controller. And the detection mechanism gets input from the sensor and from the action of the controller. And then, based on the sensor input and the controller input, you basically have a digital twin or a model of the control of the physical system. And you say, well, based on my previous measurement and based on the last control action that I sent, I expect my new measurement to be like in this range, right? So if I'm filling a water tank and I know I just, like for example, if the pump was off and I see the action to turn it on, then I expect that the next time measurement, I'm gonna see an increase in the water level of the tank of, I don't know, 1 centimeter. Let's say that my model says that if I turn on the pump, every time I take a measurement, I see a 1 centimeter up. So you can create models, right, of the physical model, and then you use it, you estimate, okay, I expect it to be, let's say, 1 centimeter up this time, and you see what do you get, and you then compute the residual. You say, well, what's the difference between what I see and what I'm getting, and then I perform some statistics on that signal. I mean, obviously, just one signal enough is probably not good. So you need to have some historical statistics to be able to make an informed decision. If you just take one action, then you're gonna get full of false alarms, a lot of false alarms. So you need some statistical test to say, well, is this significant over a period of time? And am I performing? So so we leverage the theory. So this was a collaboration with some of our colleagues that work in control theory, and there's a lot of people that have proposed mathematical models of the control of vehicles and drones. So in this case, these are the sort of like the equations of a drone given the input to the actuators, what you expect the output to be. So you basically estimate. So you have general equations, but then you have a drone that you haven't tested these equations on. So you basically first at the beginning, you estimate the parameters by giving different flight missions, and then you can estimate what the physical system looks like. So we implemented this in a couple of realistic looking settings. So we got a drone from Intel that had PX force models, and this is what we implemented here. So traditionally, this system has a middleware, so it gets the inertial measurement units and the GPS signals. They go into the flight stack, and then without our intervention, this goes directly to the actuation, to the propellers. What we did is we injected this middleware here for detecting and the attack. So we implemented an extended Kalman filter in this embedded platform to basically estimate given these inputs and given the sensor measurements and the control inputs, this is what I expect. And we implemented for the statistical test, we implemented something called the cumulative sum, the QSUM. If any of you works in or has heard the literature on quickest change detection or change detection theory, that's one of the tests to change if a signal has changed over time. And yeah, so we implemented a couple of these. So we tested this on a drone, and so this was an example of a drone. We didn't launch a GPS attack because that's, I know, I think we need to get permission for that, and it would be illegal. So what we did is we injected into the drone, we injected false GPS signals. So we created we implemented in software another module that would override the sensor measurements and send a fake GPS signal. And this was the flight that the drone was taking. So originally the drone was supposed to start here and fly up to this destination. And then we started sending the fake signal, so basically overriding the GPS signals of the drone. And and because there's a period of time where like there's some locking logic that doesn't let these signals to change immediately for the drone to take actions. After a while, there's a GPS timeout, and then our signals start taking effect. And the drone, so this is the real drone. In blue is the real direction. In the red one is where the drone thinks it is. So the drone thinks in here it thinks it is here, but it is actually here. But we are sending signals here. So because it thinks it's here, it tries to correct, and then in reality what it does is this, and then it lands in a different place. So we say, well, if we launch this attack, then yeah, you can detect it with our module. And we also launched a similar attack on autonomous vehicles. Let me skip to the interesting part because this video. Yeah, so we implemented this on a small scale car, and what we did in this case, we injected a fake video into the camera. So we took over the camera and we replayed the previous video, and then the car goes off the charts. But then yeah, we obviously also detect the attack because it's not consistent with what the control actions that we're sending, right? What we see is not consistent with what we're sending, so we detect the attacks. So we compared it with a couple of other proposed algorithms, and the interesting thing was for security, what makes it interesting is if there's an attacker that is maybe able to figure out our detection module, how it works, and if it sends an attack signal that is stealthy, that basically doesn't raise an alert, and how long can it lead the system to an attack. And we showed that, for example, previous models, if they were stealthy, they were able to, for example, in this case, crash the drone and make it, for example, decrease altitude. But with our system, if the attacker wanted to be not stealthy, I mean, if the attacker wanted to be stealthy, meaning I don't want to raise any alerts, then I can, because I have to confirm with the physics, I can only deviate a little bit. And in this case, you can only deviate this much. I mean, you can still cause an impact, obviously, because the models are not perfect, right? There's still some error, and the attacker can abuse that error to drive the system slowly and slowly off chart. So if we let the attacker attack forever, then yeah, it's gonna take over the system eventually. But if we have a fixed budget, let's say we have, in this case, we let the attack only go for 15 seconds. Then in this case, the attacker, for example, can only change the altitude from 10 meters to 8 meters, and then you go back. But yeah, and you can show that you can implement this in a real system. So we implemented it again in this car and in the drone, and our reference monitor, we call it. It's like the overhead is less than other, like several other functions that the autonomous vehicle is doing. So it can work in practical situations. So this motivates the responding, because you say, well, okay, you detect the attack, but then what do you do, right? So do you call someone to come and pick up a drone, but the drone is maybe what we're expecting is to have more autonomy. And we're probably not gonna have a human operator for like thousands of drones potentially flying in a swarm, right? So the question is, you have to have some level of autonomy as well for recovery. So what do you do when you detect an attack? So let's say you are in a safe area and then your attack starts and you drift to an unsafe space. And the question is, well, what do you do? Do you stop here? Probably not, because if this is an unsafe space, you probably shouldn't. Maybe you should try to recover. And then the question is, how do you recover when you're under attack? Ideally, you would like to maybe come back here to the safe area and stop. But what if you overshoot? So there's many things that we can consider in this problem. So we want to basically do something after detection. We want to discontinue the attack and then ideally remove the impact of the attack before a given deadline in a control system. So this was a collaboration with Penn State, the University of New Mexico, and Notre Dame. And the goal was in this case, so our motivating example, let's say, is you have a vehicle here, and you're in a highway, presumably there's another vehicle behind it, there's another incoming traffic, and then you have an attack that happens here, and you start sort of like drifting, and then you detect the attack, and then you say, okay, I need to recover, I cannot, but what are the options? Again, one option could be, okay, stop right there. If I say the attack, stop. But that's probably not the safest, because there's incoming traffic, and if you stop in incoming lane, that's bad. So maybe another way could be, okay, maybe I need to recover, come back to and then stop. But that also kind of creates trouble. There was, for example, like a Tesla accident last year in San Francisco. I don't know if you saw it, that the autonomous vehicle a Tesla just swerved into another lane of the same direction, and then it stopped. It braked. It came to a stop. And then everyone that was coming behind had like crashed. It created a crash of like, I think, 7 vehicles, and some people were injured. So the question is, okay, yeah, maybe stopping, even if it's on the same direction, is not the best solution. So the best solution in this case would be to go find, if I have a shoulder, ideally I would be able to drive here and then maybe stop. So yeah, I mean, this is a hard problem, and that's something that, like how to solve how to decide where to go, something that I'll talk about towards the end of the class. Sorry. Oh, it is a class, right? This is a, so, anyway, so, but for the moment, let's assume we know where we want to go. If there's an attack, and we want to satisfy this recovery, to satisfy several properties. We wanted to have obviously safety. We want the system to be safe. That's probably the main priority. We also want it to be robust to uncertainty. We want it to be fast so that the system can in the physical world can recover quickly. We want a low computational overhead as well. A lot of these systems are embedded platforms, so we don't want to make something that is an overkill. We also want uncompleteness and soundness. We want to always find a solution, and we want the solution to work. So there's been a couple of previous papers that have considered this problem as well. So one approach is just restart the system. So these were proposed mostly in control conferences that you say, they call it rejuvenation approaches. The idea is that I guess the motivation, well, you probably know in computers, right? If something is not working, you just restart. And a lot of the times it fixes the problem. So that can be a solution. You just say, well, I'm just going to restart and continue. I mean, of course, that doesn't remove all the attacks, but you can remove some of them. And the question is, what if you restart the system, you continue moving with your inertia, you're not being under control, what happens? So that one is it has this solution, for example, has low computational overhead, and it's complete. You always find a solution, but it doesn't guarantee safety, right? It's just sort of like a best effort approach. Not sure if it satisfies recovery either. Soundness is not guaranteed again, it's not. So yeah, it doesn't, I mean, it's, it can work for some, a subset of attacks, but not all of them, and it doesn't provide strong guarantees. Then there's the literature of virtual sensors that basically you create, but essentially, if you know control theory, you create an open loop model of the system. So you're basically saying, okay, you know what? If I detect that my perception of the system is compromised, then I'm just gonna assume I have a good model of the system and do open loop control, right? For a little bit. Obviously not forever because errors will accumulate, but I would say, well, I'm gonna work open loop and I'm gonna try to go to the shoulder of the road and that's it. And basically I don't have any sensors. I'm just given what I know about the dynamics of the system. I know that if I turn the car right, I know I'm gonna go right, so I'm gonna turn it for, I don't know, for 3 seconds at the acceleration that I'm going. I'll probably reach the shoulder and then brake. And that one achieves, it's always complete because you can always find a solution, and also low computational overhead. Maybe it's better than the restart approach in terms of safety, but it's still not there yet. It doesn't have any guarantees on safety or the speed of recovery or soundness, meaning that the response satisfies any property. And then the final set of papers that have been worked in this field are, you use a safety controller. So you say, you have basically 2 controllers, one controller for the original mission, where you use your, the mission is to go from point A to point B, and that's your main sort of like direction. And then when you think there's something off, then you switch controllers and you say, well, I'm gonna give my mission up. That's not my goal anymore. I need to go to this other controller. This is usually called the simplex architecture. So you have another controller, and then that controller takes over the system and does some safety maneuver. And that one provides better safety guarantees and soundness as well. But it has the challenges that it's not complete. And sometimes if you want to say, well, I want to satisfy some property, sometimes you cannot figure out a controller to satisfy it. And the computational overhead starts increasing because then you have to compute things online. And it's not clear that the previous work is robust to uncertainty and fast. So this is what we're tackling in our work in our task 2024, trying to maximize or stretch these things as much as possible to consider stochastic systems. So basically, we consider a system that is perturbed by noise, so our observations are not certain. And then we prove soundness and completeness for our method, and then we maximize also the probability of fastest recovery. So we formulate the problem in a way that you optimize what is the fastest that I can steer the system, the physical system, to the safe set, given my construction. So yeah, the paper in general is it has a lot of moving parts. So you need some basically database of your history, so that when you detect the attack, you can roll back and say, okay, this is the last time I had a true, like a valid perception, and then I move forward with that, so I can reconstruct my state and I know where I'm now. And then I have the model, the problem that I'm solving, the probabilistic optimal recovery. And then I have a model adaptation that it's based to make it efficient. If we want to implement it in embedded platforms, we probably don't want a nonlinear model here. So we basically linearize it at different steps. So we have different linear models depending on where you are. Then we can switch between them. And the whole goal is basically you're here, you're basically, this is your state. The attack starts at some point, and it makes you deviate from where you want to be. Let's say this is the target set, And there is some maybe okay set, maybe it's not unsafe, but it's also not where you want to go. And then maybe here, this is the unsafe set, this is where you get the accident, let's say a crash. And your goal is to say, well, I detect an attack, then I want to be able to roll back to where the attack happened and start up something, probabilistic recovery mechanism that will drive me back to the safe area. So this is basically what we're doing. And we do probabilistic recovery, state reconstruction, and this model adaptation to keep the system safe. So so we define the system as maximizing the probability that the state given some inputs reaches the target set, subject to constraints on the input, and we solve it. We also solve it online because we want this to be safe in real time and then for embedded platforms as well. So we need to solve an algorithm that is sound and complete, that is low computational overhead, and in this case, it uses linear approximations. So I'm gonna skip a little bit over the math, the technical details, but the idea is, you have a control system, and the stochastic nature is that, you have a probability distribution. So the state of the system is perturbed. Oh no, it's original. The original state is it's uncertain, so we don't know exactly where we are. It's a cloud defined by a Gaussian distribution, and then we start using reachability with the covariance of the noise, and the goal is to find, using probabilistic methods, to find the optimal state. In this case, if we want to go into a strip A and B, sort of like the optimal place that we want to go. It turns out, if you do the math, that the best solution is to go obviously to the middle, or the one that minimizes the error. So we use theoretical xenotopes for reachability analysis, so that we can make this approximation in real time. And we basically, this is basically the part where we do open loop control, and at the same time we take the Gaussian noise, and we try to go always for the middle. And we prove that this algorithm is sound and is complete. And let me just give you some examples of how it looks like. I think we can go over the details in the paper or in the discussion session if you want. So we performed this in a couple of experiments. We did experiments with a drone using Gazebo and using Ersin. I don't know if any of you have used these simulation platforms, but this is similar to Carla, but for drones. And then we used this at the time SVL was still being under development when we did these experiments back in 2023. I think SVL now, I haven't looked before the talk what is the status, but the developers were not going to be focusing on this anymore. So this is basically like an alternative to Carla. So we also did it in our small platform, and we compared it with previous work, some previous work on recovering the system using different mechanisms. In this case, we were using linear approximations with an LQR controller, or only the virtual sensors, sort of like just switching to open loop control basically. And so this is an example of our mechanism in our small vehicle. So you have no attack, and then the attack starts, and then we start the recovery. So the system goes in open loop, and in open loop, it is able to drive the system to the safe area and stop. And we also did it in SVL, which is again the sort of like the alternative to Carla. So we ran several experiments where we have the car, the attack begins, and then recovery starts. There's some swerving, I guess, but it manages to get out of the way as well, like into the shoulder, most of the times. And yeah, basically, we have several metrics for evaluating how our system compares to the other ones, to alternatives. So we have the OPR is our mechanism, the optimal probabilistic recovery, and we have this one is the real-time quadratic regulator, and this is virtual sensors. So if we want to be safe, in this case, our system comes back, and like for example, in this case, the virtual sensor doesn't recover the system to a safe space. This one recovers it to a safe space as well, but it's not always the case. So our system in the experiments, most of the times, yeah, we have tables with averages, but most of the times our system was able to drive the system to a safe space and the other ones didn't. And the other thing is that our system, yeah, it was also faster, and it was also complete, meaning we were always being able to find the solution of the system. Sometimes with the RTR-LQR, which is one of the sort of like the real-time quadratic regulator, we were not able to find solutions. So the system would say, you know what, I cannot give you a safety solution given the conditions, and I give up. After running it, after running through the constraints, they say, well, there's no solution that satisfies the safety specification, and I give up. And that's probably something we don't want. So that's the advantage of being a probabilistic recovery. We're maximizing the probability of safe recovery, so it doesn't guarantee that it is 100% safe like the previous one. But the advantage is that it doesn't give up. It gives you sort of like the best effort to drive the system probabilistically to the safe space. So yeah, so that's the motivation. And yeah, we also extended it to consider, well, what if we don't need to go completely in open loop? What if we are able to tell precisely which are the measurements that are being attacked, so that we can use the other sensors to help us? And in that case, we obviously improve. So the open loop and the closed loop, it improves the mechanism. So in the last 2 minutes, I wanted to talk about what I mentioned at the beginning. I discussed the options of going, for example, to the shoulder. But how do we define this? Like, for example, going to the shoulder. So these previous papers and all of them, they always assume somehow magically the designer of the system said, you know what? Whenever there's an emergency situation, you have to go to this target set. But how do you define that target set? I mean, it might make sense if there's a human in the loop, that there's an alert, and maybe there's a drone operator or a vehicle operator that it gets alerted and it says, okay, given what I see right now, I think this is the best solution, so go there. But in reality, this is not scalable. If we want to have more autonomy, the operator maybe is not going to be, the human operator is not always going to be there present. So we want to say, can we also offload the idea of where to go to autonomy or to an autonomous decision maker? So let's say there's a drone traveling, and then there's an anomaly detected, and we don't have a safe set. Or maybe we have safe sets, and we say, well, you know, if you're here, you have 2 options, and maybe select the closest one. But the problem is that this, in reality, in the real world, systems change all the time. So in this case, for example, there might be people having a party in one of your safe sets. So this is no longer a safe set, right? So you need to have like the decision maker before you decide where to go, where is your target set, what to do when there's an anomaly detected. You need to have some dynamic evaluation of the risks. And the question is, how do you do that? And yeah, so the previous work, first, the main limitations of previous work is that in reality, it's going to be hard to find the priori knowledge of the target sets, right? So it's very hard to always document, okay, these are all the options that you have before the mission even starts. And second, the target set will change over time. So for example, people might be having a party or something, there might be something going on in the dynamic situation, and you should have to evaluate this. So in the previous work, most of the papers in this area have considered this. You have the nominal controller, and then you go to this safety recovery controller. And what we're working right now is having this autonomous common sense agent that will tell this one, like give the extra parameters that you need, like for example, the safe set or the target set. So in this case, we would say, well, we would use an AI system that would say, well, given these two situations, I can evaluate the risk that maybe this is not a good place to land because there's humans and this one seems empty, so just go and land here. So we're actually prototyping this. We have some prototype with a multimodal LLM. And we are creating scenarios. In this case, this is a scenario in one of the simulators. So we have a drone that is flying and we have 4 buildings. And initially, all of these sets were target sets. But then we ask we give the images to the multimodal LLM and we ask in the image, like basically tell us where to land, right? And in this case, the idea is that the LLM will say in the image there are people on the rooftops of the buildings located in the top left and top right corners. The rooftops of the buildings on the bottom left and bottom right corners don't have any visible people on them. And well, one of the challenges is that they cannot sense spatial relationships well. So we supplement this with some pre-processing, with some image processing, so that we can identify specifically, spatially, where are these locations, and then we give it to the LLM, and then the LLM will make this decision. So we're currently working on this. Right now, we have a workshop paper that we just published with this idea, with some preliminary results, but we're extending this to give more reasoning accuracy and interpretability. So we're improving our prompting and the contextualization of the system. And yeah, we're also improving the way that this system is automated so that we can give it to the system. So this is an example. I think this is the paper, the particular example that we're using, and we say, well, this is the prompting that we're using is chain of thought, and then I want the response format to follow a specific JSON format so that we can then give this like the images, we pre-process them, we give them to the LLM, and the LLM in this case is Falcon, but we're also using GPT as well, and it says, well, the safest and most suitable locations for landing are the flat rooftops without obstructions and people, and the ranking, it's rooftop 2310, given some specific format that we give. So we're working on extending that in directions, and the next steps are efficiency. So right now, the models that we're using are basically in the cloud, and in the future we want them to be either on the edge or on the drone itself. So I'm working with one of my colleagues that works in the AI, so that to have some efficient models that we can query in the platform or in the edge, and then also make sure that they're robust to malicious perturbations. So yeah, so the takeaways are in this talk are that as we are providing more functionalities to and we need to be ready not only to prevent, but also to detect and respond to attacks in an automated manner. And yeah, welcome to our robot overlords. So with that, yeah, I'm open to questions, and thank you everyone for staying until the end.
Questions?
Oh, I have one.
Yeah.
Okay, so when you're talking about landing on the buildings,
Yeah.
I'm wondering if you're thinking about getting permission. Expensive building, it's gonna have its own security, and it's
Right.
gonna potentially think the drone is attacking.
Yeah,
And
yeah,
even if it's not something with security, people get paranoid of like the insurance drones that are flying over
Sure.
their houses.
yeah.
So if you just unannounced land on a roof, I feel like that's maybe gambling on who's inside the house, not coming after.
Yeah, true, this was I guess a very generic use case, but yeah, there's a lot of real world complications as you're saying. I guess in that case, the question is, like, what are your alternatives, right? So let's say there's something off. You eventually have to make a decision, right? And what to do under those circumstances. That's why probably we need this risk assessment of what are the potential like actions that you take in that situation, right? And maybe the worst case you say, well, we're not gonna allow any drones to fly in this city because we don't want any, like, some of the potential risks that maybe you're proposing in the future. Yeah, let's imagine this is Amazon is releasing a fleet of drones for delivery or something like that. And one of the recovery options is maybe saying that, and you say, well, the city planners, they don't like that. So yeah, the option would be in that case not to let them fly. But yeah, this is just one example. I mean, you can think of this also in combat situations. Maybe there's like in a forest and you want to maybe get to land away from the enemy or things like that. So yeah, this was just a motivating example, but the general framework is more general. Yeah, I want to basically find the safe areas in different contexts to decide where to go, or what to do.
So do you think it would make sense for cities to have like registered drone plans so that if you're an operator, you can let an official person know that, oops, I've had an accident and I need to land, like an FAA for drones?
Yeah,
But
that's a good question. I don't know. I think probably I would need to collaborate with someone, city planning or something like that. Yes.
They need to be registered.
Well, in the AV safe recovery example, I was curious about how the system would deal with finding a safe zone in an area where there wasn't a shoulder, like on a bridge or like a multi-lane highway or something.
Yeah. It's a tough crowd, yeah. No, I agree. This is a difficult problem, and that's why I said at the beginning, all of this literature assumes that you already know you have a safe space. Like you have a target set. I don't know. Somehow, someone told you before the mission started. If something goes off at this particular location, this is your target set, right? So, if you have that assumption, then yeah, it works. In reality, as you say, maybe there's no safe option. Like if you're in the breach, I guess if you're in the breach, maybe the safest option is just to stop where you are, I would imagine. So I guess you need to either have someone before the mission starts define the safe sets, and in this case, yeah, it would be something a little bit more constrained in that situation. Or what I'm proposing, hopefully in the future, we'll have this common sense reasoning that will say, you know what, the bridge ends up over there. Maybe I'll try to go a little bit until the bridge ends and try to find that place to stop. But yeah, no, I think those are the key answers. Yeah, key questions to ask. I would say if there's a drawback in this situation is how to find the safe area, right? It's gonna be contested, and you need to have multiple factors play into that situation. Yeah, not only engineering factors, but also like I guess socio-technical factors, as you were saying, right? Maybe in the drone landing in a building is not an option, right? So yeah.
Thanks.
Yeah.
I was just thinking about the optimal probabilistic recovery. For example, in computer systems, when you want to have system restore points, you have to save like an image of the whole software and the perfect path. In terms of drones, you'd have to save the path that it was meant to go on. And then whenever an attack comes on and then it needs to recover, you have to store this information somewhere. Would you know, like, at what intervals it would be best to store this image of the software and the path for the drones perfectly, so that, I mean, it also has to iteratively happen as often as possible so that when the attacks happen, it can recover as quickly as possible?
Yeah, I think, so I think you're mentioning two things, I would say. One is the history of the state of the physical state, and the other one is, I guess, I don't know if you're referring to this, but the other one is I don't know, maybe I'm imagining things, but because in security, sometimes you want to reimage a machine and you take it back to an initial safe position.
Yeah.
So that for me, that one would be similar to the restart option. So I don't know if you were talking about that one or not. So there, I think there's two possible interpretations of what you said, and I want to make sure I understand it correctly. One is to say, I'm under attack. I'm going to basically reimage the system. Basically means I'm gonna remove it. I'm assuming I have a hypervisor or something underneath, and it says I'm gonna remove the whole operating system and the whole machine basically that you're running because it's compromised, and I'm going to look back to my database to the previous safe, the safe measurement of your system where I know you didn't have malware and then I put it there. Yeah. If that's what you were asking, then that solution is similar to the rebooting scenario. It would take longer because it's not just rebooting. You're reimaging the system is basically reinstalling everything. The other one the one that I was mentioning here is this historical data checkpointing, which is not a checkpoint of the image of the virtual machine in this case, but it's a checkpoint of the sensor history of the physical sensor. Like I know I'm in position X, Y, Z. Like I was at height this, at latitude this, longitude this, at this point in time, and then like 5 seconds later I was here. So what I was talking in this slide was about that history, because if, let's say in the car example, if you're drifting because of a GPS spoofing attack, let's say, or in the drone example, then if you take the latest measurement, then you know you're already under attack. You're already drifted. So what I was saying here is that you need some historical measurements so that you can try to reconstruct where the anomaly started. So you go back in time using change detection theory methods for a signal. You have a physical signal, and you use change detection theory to find, okay, there's an anomaly, and then you go back to the change point that people in change detection theory call it the change point. And then you go here, and then you say, okay, now starting here is when, I'm in time here, but I know I cannot trust this sensor measurement. So I go back here, and then once I'm here, I use open loop methods, basically a simulation of the system, say, okay, given my last trustworthy measurement and the control inputs that I've been given, I think I'm over here. And then I switch to the safety recovery or something like that, yeah. So that's what I was mentioning. So, but yeah, I think that both, in general, yeah, when you're recovering, you either need both options or one or both. Yeah, so this one is for the physical process. The other one is more digital, more classical security. Like there's something bad, you just reimage, and you hope that will remove your system from the malware from the system. Yeah.
I'm curious about in the recovery options that had either a sensor involved or, if I'm understanding this correctly, like essentially kind of a duplicate controller to take over if the nominal controller gets messed up.
It's not. It's a different controller with a different objective.
Okay.
So the first one is I want to drive all the way from, I don't know, from Davis to Santa Cruz.
Yeah.
And the safety recovery is I just want to get to the target set because
Okay.
And I use different control methods. Maybe the other one is using NPC and this one is just using I don't know, like LQR mechanisms. Yeah, anyway.
Okay, so would that be potentially, I guess, at risk of the same attack that happened to the nominal controller, or is there normally something different about it that it wouldn't like?
In this case, I assume that, so in this case, I was assuming attacks to the perception system. So the safety controller is also subject to that attack.
Okay.
But the difference is that now that I know I'm under attack, I am using this, what I was telling you, that I'm looking the sort of like this open loop control, so I don't trust my sensors.
Right, okay.
And I guess that's the difference. Yeah, I changed the objective, but I also changed the method. Like, for example, the sensors that I use or the perceptions that I use for the computation of the control action. right?
Okay, that's helpful, thanks.
Yes.
Thank you for your presentation. I want to know some conditions that, for example, two AVs are under attack by each other. And I think if they behave similarly, cannot be easy to, for example, modelize their behavior. For example, two AVs behave similar for getting away from each other. But I want to know how this model can handle these conditions. For example, both of them want to switch their way, but for example, if both of them switch their way, as a result, the crash will be happen in the future distance. You know, I think.
So you're saying if two of them are under attack and they switch, or what?
Yeah.
If two of them are under attack, and I guess what's the question? Like if you,
For example, they behave similarly,
yeah,
and if they behave similarly, for example, you you mentioned something that, for example, one A switch its way to, for example, run away from the accident.
yeah.
But if both of them have similar actions,
Okay.
I think
Well, everyone goes to the same target set and they crash or something like that.
Yeah.
Yeah. I guess that's a risk, and I think that's why. Yeah, I guess I didn't mention it here. And actually, yeah, that's true. We didn't consider multiple attacks. That's probably a good point. Multiple attacks simultaneously in different agents. But for one agent, one thing that I didn't mention, but the details are in the paper, is that you want to make sure that the system, that the recovery, sometimes you're gonna get recovery on a false alert or a false positive, and you want the system not to be less safe than if you don't. So then if you don't have the attack. So yeah, so I didn't put it here, but yeah, we have a lot of work on also proving that under a false alert, your system is still safe, but assuming only, we were only considering one attack. If you're considering, I think it would be interesting to consider, in my work, I've never considered the swarms yet, but maybe that's something to consider in the future. Yeah, if you have a swarm or you have multiple autonomous devices or vehicles or drones, and the attacker is able to trigger responses of all of them at the same time, the response mechanism has to be such that you minimize the chances of making the things worse, right? So it's a very good point. In this scope, we only had one, and we were assuming only one. But we always have to be. It's a good point in security that you always have to be worried that the security can fail in two ways, right? So you can fail to detect the attack, or you can make the system worse by your security, and in that case, you're taking that second consideration, right? So if the attacker can somehow exploit the system and make, if we didn't consider, as you say, maybe all of them have the same target set, and because they're not paying attention to the sensors, everyone's gonna crash, which would be like, it would be like a big catastrophe. It's a good point. I should have a future in security threat modeling.
Any last pending question?
Yeah, just one question. In the end, you mentioned that current recovery algorithms are online, so it's outside the vehicle. My question would be, is it even?
No, these ones are in the vehicle. What I was discussing at the end is the one with the LLM.
Yeah, but is it possible to have like systems run outside the vehicle themselves, or would there be some legal requirement? Because from cars, for example, I heard that it is necessary to have all the safety features being done on board, so there's no necessity for having a connection to.
Right, and I think for vehicles, it should be okay to have these more complex models because they're more powerful. What I was looking at, the particular model that I was looking is for drones that are going to be like more resource constrained, and there's been a lot of work in particular of having edge devices. An edge device is basically like a device, maybe a super drone that is more powerful. So maybe you have, for every 10 drones, you have like a super drone that has more resources, and then you would put it there. And so that it helps with the computation and you don't need to go all the way to the cloud in that scenario. But yeah, in principle, yeah, I think we basically what I'm saying, at the moment, our prototype uses the cloud, but in the future, as you say, yeah, we want to be either in the vehicle or nearby in an edge device. So that's what we're working right now to make sure that the AI models or the generative models or the foundation models that we're using are on device and not on the cloud yet.
Well, I want to thank our speaker, Alvaro, for this interesting presentation. A round of applause.